Oh, they'll probably lose anyway.
You were gonna lose because my bishop is so.
Yeah.
Do you see what's going on with the bishop?
Oh, yeah.
They can control this diagonal.
That's gonna lose my queen.
I'm not gonna bother your queen.
No.
I'm gonna leave it to you because it's like has nothing to do with.
You're right. Once I move my queen out of check, you're gonna have to
I'm not sure how you can let's say I check.
All right, let's get started. So I was talking to you about trees. We counted trees. We proved that the number of trees that are labeled, and the vertices are labeled 1, 2, 3 up to n. We proved that the number of trees like that, on n vertices labeled, is n to the n minus 2. Okay? And today I want to talk about a much more general problem, which is the problem of counting the spanning trees of a graph. Okay? So let's talk first about what that is. So a spanning tree of a connected graph G is a set of edges set of edges which connect all vertices and form no cycles. Okay. So I don't know if my graph is like this. Then there's many spanning trees, but for example, this is a spanning tree, or this is a spanning tree. These are spanning trees. So what's not a spanning tree? There's two ways to not be a spanning tree. One is that you don't connect everybody. So, this is not a spanning tree because you don't connect the 4 vertices. You only connect these 3 to themselves, but they're separated from that one. So that's not a spanning tree. And for example, this is also not a spanning tree because even though it connects everybody, it forms cycles. Okay. So here's an easy fact. You should think about it and convince yourselves, but it's not too hard to see that if G has m vertices, then a spanning tree must have exactly n minus 1.
Vertices?
Edges, I'm sorry. So a spanning tree must have n minus 1 edges. So I'll let you think about that and convince yourselves of that. And so what our goal for today is to count them, count the spanning trees. Okay. So we're going to do the following. So given our graph, which has some set of vertices and some set of edges, we're going to orient the edges in any way. Orient the edges arbitrarily. Doesn't really matter how we do it. So I don't know. Maybe in this example, I'll do it like this, like this, like this, and like this. I just choose some orientation for each edge. And now I'm going to make 2 matrices. So the incidence matrix of the graph is it's a V by E matrix where So here I have my vertices, here I have my edges, right? And whenever I have an edge in the graph from vertex I to vertex j, and let's call this edge E, then I'm going to look at column E, and I'm going to look for entries I and j, bigger maybe, and I'm going to put a 1 at I and a -1 at j. And then the rest of the column is 0. Okay. So let's do that over here. So what's the adjacency matrix? Sorry, the incidence matrix. So I should give names. Let me use the same names that I used here. So I name my vertices A, B, C, D, and those are going to correspond to they're going to correspond to my rows. Okay. A, B, C, D, and then my edges are going to be 1, 2, 3, 4, and 5. Let's see how did I label them here. I call this 1, 2, 3, 4, 5. And so basically in this matrix I just say, edge 1 goes from A to B, edge 2 goes from A to D, edge 3 goes from B to D, edge 4 goes from C to B, and edge 5 goes from D to C. Okay? And then the rest is zeros, and I'm not going to draw them because it's a little bit easier to read it like this. So this is the incidence matrix. And then I'm going to define the Laplacian matrix. Is M times M transpose. Okay. So, if you think about that, I'm going to imagine multiplying M by the transpose, right? So the result is going to be M is a V by E matrix. The transpose is an E by V matrix, and so when I multiply them, I'm going to get a V by V matrix. So let's do it. I mean, so for example, what is this entry? This entry is basically this row dot product this row. So 1 times 1 is 1, 1 times 1 is 1, so I get 2. And why do I have a 2 there? I have a 2 because I have 2 1s here. So let's do the BB entry. Okay, so this is the dot product of this row with itself. So it's going to be 1 plus 1 plus 1, which is 3. And I have 3 because I have 3 1s here. And similarly, I have 2 1s here and 3 1s here. Okay? So then I want to say that Lij is, if I is equal to j, then this is going to be the degree of, actually let's call them BMW so they sound like vertices. And so I'm saying that the diagonal entries are just the degrees of the vertices, right? How many edges are coming out of those vertices. Now what about the entry AB? Well, this is going to be the dot product of the row A and the row B. So when you take this dot product, you get 1 times -1, which is -1, and then 0, 0, 0. So I get a -1. And I get a -1 because I have an edge from A to B. And similarly, when I do the dot product of A and C, you'll see that there's no edges from A to C, so that product is 0. And there's one edge between A and D, so I'm going going to get a dot product of -1, and so on. Okay. And so what I'm going to get here is the minus the number of edges from V to W. And actually, if you notice, this doesn't notice the direction of the edges at all. And so what I'm going to get is just this matrix that basically tells me which vertices are joined by edges. So the only zero here is from A to C or from C to A, and that means that this is the only missing edge of the graph. Okay. And I'm only going to consider graphs without repeated edges, without parallel edges, but if you have parallel edges, that's why you need to say number of edges from B to W if you allow yourself 7.
What do you mean by parallel edges?
So parallel edges are like this. These are two parallel edges in a graph. So, you know, I am allowed to do this, and if I had this, then I would see a -2 instead of a -1 in my Laplacian.
I just want to check. You just place these arrows on the graph however you want it, right? There's no orientation.
Right, so let's talk about that for a second. So I said let's start with a random orientation. So to what extent does that choice matter? If I chose a different orientation, well, all I'm going to do is change the sign of a column, right? So M depends on the orientation, but if you notice, L does not depend on the orientation. Especially if you look at it from this description doesn't see the orientation. And actually, it's L that's going to be more important to us. Yep?
Parallel edges have to have opposite orientation, or they can be the same as well?
Parallel edges could have the same orientation, or opposite, it doesn't really matter. I mean, really, the only reason that I picked an orientation is just so that I know where to put a 1 and where to put a -1. But it doesn't really matter where I put which one. Okay, so no, let's make some remarks. Note, L is symmetric, right? Let's go from either from this or from this, right? If you take the transpose of this, you're going to get M transpose back. L is symmetric. And the other thing that you should notice is that L is singular. Can you see why L is singular? Singular meaning not invertible. One easy reason why L is singular is that if you add the rows, you're going to get 0. Why is that? Because this number 2 tells me there's 2 edges leading from A, the one going to B and the one going to D. There's 3 edges going from B to A to C to D, etc. So the number of -1s is going to match exactly the degree. So L is singular. Okay. And so okay, that might seem a little bit strange why I want to define a matrix if this is not a linear algebra class but a combinatorics class. But it'll make sense in a second. So let me define a principal cofactor of my Laplacian is obtained from the Laplacian by removing row I and column I for some I. Okay. So there's n cofactors where n is the number of vertices. And so here's the theorem that I would like to prove. This is called the matrix tree theorem. And it says that the number of spanning trees of a connected graph G equals the determinant of any of the cofactors of any principal cofactor of the Laplacian. Okay. It's a theorem due to Kirchhoff in the 1800s. Kirchhoff was a physicist, actually, and this is all motivated by electricity flowing around a circuit. So let's see what that theorem says here. In this example, the number of spanning trees of this graph is, we're supposed to take this matrix and just delete any row and the corresponding column. So for example, we could delete the fourth row and the fourth column. Okay. So, okay, you guys know, but maybe not everybody in Colombia knows that the dean of science wrote this book called Linear Algebra Done Right. And one of the tenets of that book is that you can do a lot of linear algebra without ever talking about determinants, and that maybe you should. So, okay, that, you know, to some extent I agree with that. There's a lot of linear algebra that you can do, and it's a lot more elegant and sometimes more powerful without determinants. But this is some place where we're going to have to use determinants, because we actually care not just about whether the determinant is 0 or non-zero, which is, you know, whether the matrix is invertible or not. We actually want the number. We want the determinant, right? If we want this answer. Okay. Okay, so I don't know. Maybe you haven't computed a determinant in a while, but so remember, you go like this. So 2 times 3 times 2 is 12. Plus this times 0 is 0. Plus this times this is 0. Minus 0 minus 2 minus 2. 8. So this says that this graph has 8 spanning trees. Yeah?
So that was called the principal cofactor?
Yes.
Why the abbreviation p-val?
It's principal. It's shorter. Yeah. It's just an abbreviation. Okay, so is it clear what the theorem says? It's a very nice theorem, surprising theorem, that you can compute spanning trees through linear algebra. Okay. So, actually, let me say something else, because there's another formulation of this, which is that if the eigenvalues of the Laplacian are lambda 1, lambda 2, up to lambda n minus 1 and lambda n. But I want to remark that because this matrix is singular, at least one of the eigenvalues has to be 0. Okay. One reason is that the determinant is the product of the eigenvalues. So if it's singular, the determinant is 0, so one of the eigenvalues must be 0. So if the eigenvalues are these ones, then this number is 1 over n times the product of the other ones. Okay. So this is an alternative formulation of the matrix tree theorem, and I don't know, maybe, I mean, at some point in life you learn how to compute eigenvalues in linear algebra. This is a reason that combinatorials really like to compute eigenvalues, and it's really important, right? Because we actually need them to answer this question. Okay. So this is what I'm going to prove next. Okay, so the proof is going to proceed in 3 steps. Step one is something called the Binet-Cauchy formula. So we're going to consider matrices A and B. And I'm going to draw them like this so that I remember their shape. Here's A, and here's B. And A is m by n, and B is n by m. Okay? Now, basically what we want to do, I mean, for example, if m was equal to n, then what would be the determinant of AB? If these are square matrices, if these happen to be square matrices, then the determinant is multiplicative. The determinant of AB is the determinant of A times the determinant of B. Okay? So that's a nice formula if these are square matrices, but if they're not, then we can't really apply this because we can't take the determinant of either of these matrices. And so then what do? So here the Binet-Cauchy formula comes in. And here I'm gonna, here n should be less than n for this to make sense. Okay?
When you give that number 1 over n times all the lambdas, are you throwing out all the lambdas that are equal to 0, right? Or
So the question is, do I really mean n minus 1 or should I throw out all the zeros? It turns out, and it's a corollary of this theorem, that there's only one zero. Because if the graph is connected, then it has spanning trees.
yeah.
And if it has spanning trees, then this is non-zero. Actually, it's possible to show that if it's any graph, then the number of zeros is the number of connected components of the graph. So because our graph is connected, then I only have one zero here. Okay, so Binet-Cauchy, it basically says the following. Okay, well, if you don't, I mean, it's kind of, so if you try to just impose that the determinant of A times B is the determinant of this times the determinant of this, well, we need to force this to be square and this to be square. Okay, and so what I'm going to do is just make a square matrix out of this one by throwing out columns. And then do the same to B and just,
Draw the same row.
yeah, so maybe it's going to be clearer if I just write it instead of trying to say it like that. So I'm going to look at every subset of n, of size n. Okay? So I choose m of the columns here, and then I take the determinant of A restricted to those columns. That's a square matrix now, so I can't take the determinant. And then I choose the same columns in B, and I take the determinant of that. And that's the formula. And just to make sure we're clear, so A of S means that you take your matrix A, okay, and then you choose some of the columns, right? S. So I don't know, maybe S consists of this subset, this, and this. Okay, this. These are the columns that you choose, and then A of S is just taking only those columns. Okay. And that's going to be a square matrix.
Question.
Yes?
Is that E of S, is that not ambiguous because S is a subset of N? So we have to choose.
Right, so how should I interpret B of S? So in B of S what I do is that S is a subset of the rows, and then I delete those rows. So A of S should be interpreted as keeping the columns in S. B of S should be interpreted as keeping the rows in S. Okay, so there's several proofs of this. I want to show you a proof that I like. that's kind of slick. And it does the following. So I'm going to consider the following matrix. I'm gonna do this. I'm gonna put my matrix A here. Then I'm going to put an identity matrix here, a zero matrix here, and an identity matrix here. Okay, and maybe we can write the sizes of these things. So this is M. This is N. This is M. This is S. Okay, so that's a matrix. I'm allowed to do that, right? Now let's consider another matrix. Like this. Okay. And so what I'm going to do is that I'm going to now put A here, 0 here, minus the identity here, and B here. Okay? And because this is the opposite of the shape of this one, this is the shape of the transpose, so I can do this too, and this is also a square matrix. So again, this is M, this is N, this is N, this is N. Okay? Do you remember seeing block matrix multiplication?
This looks really similar to a homework problem in the linear algebra class that was the question.
Yeah?
Yeah.
So it turns out that you can, maybe you've seen this, maybe you've forgotten, or maybe you've never seen it. You can multiply matrices just by pretending that these are numbers and multiply, as long as all the sizes match. So for example, how would you multiply this if these were numbers? You would say I times A minus A times I. That would be this entry. And what shape would it have? I think it would have this shape. You take an m by m and an m by n, that's m by n. And if you take an m by n and an m by n, that's also m by n. So that means that you can multiply I times A, you get A, because this is the identity. You can multiply A times minus I, you get minus A, and so you're going to get 0. Okay? Now, what do I get when I get I times 0, that's 0, plus A times B. So I get AB here. Question?
Sorry, you multiply A times minus I?
Yeah, I can multiply A times minus I. Because this is m by n and this is n by n.
Oh, okay.
Now I can multiply 0 times A and I get 0 plus I times minus I get minus I. Right? And then 0 times 0 plus I times B is B. And I checked ahead of time that the sizes match. I'm doing this a little bit fast, but the sizes do match and this makes sense. And this block matrix multiplication tells you that if this makes sense, then this is correct. And if the sizes match, this is the correct answer. Okay, so why do I do this? Because, okay, here the sizes are the same, right? So m by n, n by n. So why do I do this? Because I'm going to now use the fact that these are square matrices. And because they're square matrices, I can use that the determinant of this equals the determinant of this times the determinant of this. Right? Now, what is the determinant of this matrix? Actually, I'm very lucky that this is the identity, so I get 1s along the diagonal and 0s below the diagonal. So this is an upper triangular matrix. It has 1s on the diagonal, so it has determinant 1. Okay. What is the determinant of this one? Well, you see, here all the action is over on this side, right? But on this side, I just have 0s and then this minus the identity, right? Now I have to remember what is the determinant. What I'm supposed to do is basically choose every choice of n plus n entries, one on each row, one on each column, multiply them, and put in the sign of the permutation. Actually, I'm gonna be using this so much that I'm gonna write it down. So the determinant of a matrix, let's call it C, so it doesn't sound like that one over there. What you do, and let's say that C is n by n. What you do is that you just sum over all the permutations of n elements, and you take A1 pi 1, A2 pi 2, up to an pi n, and then you multiply by the sign of the permutation. So how can I do that here? I need to choose n plus n entries that are in different rows and different columns, and that are not zero. If I have zeros, then there's no contribution. So you see, I have to choose all of these n entries in minus I. And if I have to choose these ones, then I cannot choose any of the ones in B, because they will be on the same row as one of them. And so I have to choose these guys, and then I choose here whatever I want. So what I get is just the determinant of AB times some sign that is either 1 or minus 1. So this is plus or minus the determinant of AB. So maybe you see where I'm headed. I want to show that this matrix has this determinant. So I think that the determinant of this is the right-hand side. So let's make that argument. It's going to be just kind of an argument by picture. So what I'm going to do is the following. I'm going to say, okay, consider a term that contributes to this determinant. Now this is 0, this is minus I, so it looks like this, and this is A, and this is B. So how can I get such a term? Well, you see, here, among these m rows, I have to choose m terms. Right? I have to choose m terms to multiply in my permutation, which means that I have to choose, I don't know, some entry here, let's say some entry here, okay? Let's say that's m of them, and multiply. So these two are going to be two of my factors in here. Okay? But I have to choose m of them because there's zeros here. And so let me just call this set that I just chose here, let me call it S. Okay? So then what happens? What happens is that I need to choose one entry in each one of these columns. Right? And I already chose in this column, and I'm claiming, I'm saying that in S I only choose these two entries, which means that in this column I didn't choose anything yet, so I have to choose this minus 1. Here I chose blue. Here in this column I'm not going to choose anything up here, so I have to choose this column. And then here I choose the blue. Okay. So what are the columns here? These are precisely S complement. And I have to choose the minus 1s in S complement. And that means that I already covered S complement in the rows. So I already chose entries in the top rows, I already chose entries in S complement, but I'm still missing entries in S. So which ones should I choose? Well, I can choose whatever I want, but it's not going to be ones on this side, it's going to be over here. So I don't know, let's say that I chose this one and this one. And I can choose any possibility as long as it's in the columns, in the rows of S. And so you see what I'm doing is I'm choosing a set of S, I'm choosing some permutation of this submatrix, which is A of S. What I have here is precisely A of S. So I'm choosing some permutation in A of S, and I'm choosing some permutation in this matrix over here. And that matrix is B of S. Okay? And so what I'm doing is looking at all the ways of choosing some permutation here, choosing some permutation here, and then putting -1s in the rest of the permutation. And so what I end up with is some, I get this basically. So the determinant, at least this argument shows the determinant to the right-hand side, except you might be off by some sign because of all those -1s that are going around. And so you have to be a little bit more careful and just count the -1s and make sure that this works, but trust me, it works. And so this is the proof of the Binet-Cauchy formula. So we have the Binet-Cauchy formula, and we can use it. There it is. So that's step 1. Now, yep.
So where does the sum come?
Say that again.
The sum?
Oh, the sum is because I can choose, when I choose, I started by saying what are the m entries that I choose in the top m rows, and those can be in any m subset of the columns here. So S could be any subset of size m of the columns. And that's why I have to sum over all the possibilities. But the point is that once I choose which columns I use here, then I have to use the same rows here, which is why I only have a single sum. Okay, so that's the first step. And so what am I trying to do? Actually, I think it's more useful to do step 3 first, and then we'll see what step 2 should be. Step 3. We were trying to compute the determinant of the Laplacian and show that it's the number of span entries. The determinant of the Laplacian, which is the determinant of m times m transpose. Now, that's not quite right, because remember that the Laplacian is singular, so the determinant is 0, and so I had to remove, I don't know, let's say the last row of the last column. So here we remove last row, last column. Okay. So in other words, what I'm thinking of is that I'm just looking at this part of the matrix. Right, forget about this part of the matrix. Okay. I remove the bottom row, the bottom column, and so this is going to be L0. Right? And this is what gives me the right answer. Well, if L is m times m transpose, then it's not hard to convince yourselves that L0 is just the same thing as M0 and 0 transpose, where here I just delete the last column. Here I remove the last column, the last row. I'm still going to get the right shape, right? A 3 by 5 plus a 5 by 3 is a 3 by 3. Okay, so I have this, and I want to show that this is the number of spanning trees, and this is asking for me to apply the Binet-Cauchy formula. So the Binet-Cauchy formula tells me that I should take sum over the subsets of what's n. N in this case is the edges, right? And the size of S should be, in this case, it should be this height, which is the number of vertices minus 1. And then I'm supposed to do determinant of M0 S, determinant of M0 transpose S. Okay? Okay. Now what's this? This is the sum over the S and E of size V minus 1. Now this is just the transpose of this, right? They're the same matrix. It's flipped over, but that doesn't change the determinant. So this is the determinant of M0 of S squared. Okay? And you see here I'm summing over subsets of size V minus 1. So in particular, the trees count, because the trees have size V minus 1. And so what I want to show is that if you're a tree, this is 1. And if you're not a tree, this is 0. Okay? And so let me write here this is step 3, but then the step 2, I wanted to motivate step 2. So step 2, what I want to show is that the determinant of M0S is plus or minus 1 if S is a spanning tree. That's going to be 0 otherwise. And if I prove this, then basically I'm going to get that only the spanning trees contribute. So I get sum over S spanning trees. And I get a sum of 1s. So this is going to be the number of spanning trees. Okay. So I will be done as soon as I'm able to prove this thing right here. So this is the last thing to prove. I don't need Binet-Cauchy anymore. So this is what is left to prove. And so let's prove it. Let's make some room here. So let's prove step 2. So assume S is not a spanning tree. Well, if you have V minus 1 edges and you're not spanning, then you kind of wasted edges by wrapping into yourself. You're not a tree. You have cycles. So since the number of edges is the correct number for a tree, you see, if you're not a tree, then what you're doing is you start with a tree that connects everybody, and you're taking edges from the tree, you're taking them out to disconnect the graph, and you're putting them back on something that is already connected. You're going to form a cycle. So S has a cycle. And, you know, maybe we can consider what that looks like over there. Say, I don't know, 3, 4, 5 in that example. So 3, 4, 5 is a cycle there. So how does that look in M0 of S? In M0 of S, I have my submatrix A, B, C, 3, 4, 5. Okay. Let me draw it in green so that I remember that this is M0 of S. How does that cycle look? Well, it looks like, in this case, 3 goes from B to D. 4 goes from. Actually, let me do a. It doesn't really matter, but let me do the example of 1, 2, 3, which is going to be a little bit clearer. And then we'll talk about the other case. So I have a cycle 1, 2, 3, right? And so if I look at columns 1, 2, and 3, that looks like 1 minus 1, 1, 1. Actually, no, it's not really any different. I think whether I chose 1, 2, 3, or 3, 4, 5, it's the same thing. Now, I think there's a slightly better way of explaining what I'm about to explain, which is this. The orientation didn't matter. Right? So far the computation works no matter what the orientation is. So let's change the orientation so that my cycle follows the traffic of those edges. Okay? So let me go like this, and let me switch the orientation of this guy to face the other direction. Okay. So what I'm doing is this was edge number 2, so I'm just changing the sign of this and this. And the reason that that's nice to do is that now I claim that the sum of the columns of this matrix is 0. And why is that? Because what is the sum of the numbers in row A? It's a 1 and a minus 1, and the 1 is because 1 comes out of A, and the minus 1 is because 2 goes into A, right? And so this minus 1 and 1 just tells me I walked into A and I walked out of it. And this says I walked into B and I walked out of it. And because this is a cycle, you're going to, for each vertex, you either walk in and out of it, or you don't touch it at all. And regardless, the sum of the entries on each row is equal to 0. So that means that this sum of the columns is equal to 0, meaning that the columns are dependent, so the determinant is 0. Okay, so that's if you have a cycle. Now what if you don't have a cycle? So what if you are a tree? And let's choose a tree, and maybe so that it doesn't look like I'm cheating you, I'll let you choose the tree and we'll do the argument. So I'll let you choose any spanning tree of this graph. Somebody. What are the numbers?
135.
1, 3, 5. So I want to show that that determinant of A, B, C, 1, 3, 5 is either 1 or minus 1. Okay? So let's see how that looks in the matrix. So again, 1 goes from A to B, 3 goes from B to D. So D, I think I'll draw it, but it falls out of the matrix. And then 5 goes from D to C. Okay? So then, I mean, you made it too easy, which is, of course, it's not your fault. But you see the tree that you chose actually is upper triangular, which is why this is clearly the determinant is clearly -1 actually. So maybe we can pick a slightly harder example. Let's say by let me change 5 for 4 to make it a little bit harder. So if that's 4, then 4 goes from C to B. Okay. And then that's at least not obviously either upper triangular or lower triangular, so I have more to say here. Okay. So what am I going to say? I'm going to say that no matter what you chose here, there's going to be a column that only has one non-zero entry. In this case, it's 3. Why is that? The reason is that in my spanning tree, D is connected to somebody, right? Because D is connected. Let's draw the graph here. So 1, 3, 4 looks like this. D is connected to the rest of the tree, and so that means that there's an edge, in this case 3, that has an entry here, and therefore in my matrix only has one entry. Right? And so I choose that column. So here, column 3 has only one entry, which is not 0. And then I do this expansion by cofactors that you do with determinants. Okay? Or, I mean, even that's a little bit of overkill. The point is that if you're going to try to choose a permutation such that you hit every row and every column, then you have no option but to choose this guy, right? Every term in the determinant has to include this guy. And so that means that this determinant is equal to plus or minus what you get when you delete this row and this column. So you get A, C, 1, and 4. Okay? And you make the same argument. You say, well, here again, some column, in this case it's either, but some column, let's say column, I mean, what we can do is this. We can say, okay, so I took care of D, now D falls out of the picture. Okay? D falls out of the picture, now my matrix contains A and C. Okay? But then again I say, okay, well, you know, what I have, if I forget about D, what I have is still a spanning tree of A, B, and C, so B has to be connected to somebody. Right? And so, in this case, B is connected to C, let's say, and so that means that this edge is connecting C and B, which kind of fell out of my matrix. It's like B is, D was out and now B is out, okay? And so now I say, okay, well, the edge 4 went from 1 to -1, which is in B. This is out of the matrix, and so therefore, again, I can say, well, this column 4 has only one entry, which is not 0. And so then again, I can kind of cross out, and here I crossed out this row and this column, here I crossed out this row and this column, and I basically can keep doing this until I just get a single 1. So you get plus or minus just a matrix that only has a 1 or a -1. So you get plus or minus 1. Yep.
Here instead A, by columns, do you mean the rows will send to 0? Like the row A?
So the
the
question is if I do mean this, and actually I do mean this, I mean that the sum of the 3 columns is 0.
Okay.
Which is the same as saying that in each row, the entries of that row.
Okay, alright, I see the same column. But in Combinatorics we have S has a cycle, but it seems like there we're assuming that S is a cycle.
Okay, so here, if S has a cycle and has other stuff, then what happens is that the other stuff is elsewhere. But when it comes to, let's see, what exactly do I want to say here? What I want to say is that the columns 1, 2, and 3 are dependent. And the other stuff might not be. But you have a dependence between these three columns. The columns in that cycle are dependent. And that's already enough to know that the matrix is not invertible, because you have a dependence between the columns. Yeah, thank you for that. That's a good point. Okay, so this is some kind of somewhat intricate argument, but it shows that it shows my step 2, and that was what was missing, and so therefore I'm done. Okay. Maybe it's worth making explicit what I just did here, because many of you think a lot about polytopes, and many of you know the word unimodular, and what I just proved is unimodularity. So let me say it in that language. So a matrix is totally unimodular if all determinants of its minors are 0, 1, or minus 1. And actually what we just proved is that if you consider the matrix of the n by n choose 2 matrix, consisting of all the possible edges, 1 minus 1, 1 minus 1, etc. All the ways of putting a 1 and a minus 1 here. This argument shows that every single minor here is either 0, 1, or minus 1. So this is kind of a prototypical example of what a totally unimodular matrix looks like. Actually, there's a theorem, and I believe it's due to Seymour, but I should check. But there's a theorem saying that if a matrix is totally unimodular, then it either comes from a graph or it comes from a co-graph, which is kind of like a dual version of this, or there's a few exceptions. Okay, so basically, this theory of totally unimodular matrices is very nice. It plays an important role in polytopes, in Erhard theory, and so that's something good to keep in mind if you ever have to think about these kinds of things. Okay. So this matrix is totally unimodular. Okay. So that's a theorem. It says that we can use linear algebra to find the spanning, to compute the number of spanning trees of a graph. But now we want to see if this theorem is any good or not. Right? This theorem is only as good as what you can get out of it. That's a pretty theorem, but let's see if we can prove some nice things with it. So let's consider an example. What if my graph is the complete graph? Okay, so this is the complete graph, meaning that I have n vertices, and then all of them are connected. Every pair is connected by one edge. Okay. Complete graph. So how many spanning trees does it have? Let me number here 1, 2, up to n to remember that there's n vertices. So to compute the number of spanning trees, what we should do is understand what the Laplacian looks like. So what does the Laplacian of the complete graph look like? Well, remember the Laplacian is an n by n matrix. remember, down the diagonal I put the degrees of the vertices. So how many edges come out of vertex 1? N minus 1, right? 1 for each other vertex. And by the symmetry, I get n minus 1 everywhere. Okay, every vertex here has degree n minus 1. What about the off diagonal? Well, the entry here is minus the number of edges from 1 to 2. And there's 1 of them. And actually, you see that because every pair is connected, that means that every entry is minus 1 off the diagonal. So, minus 1, minus 1, minus 1, minus 1, etc. Okay, so that's the Laplacian. And so what I should be able to do is compute there's two formulations. Either I delete this column and this row and I compute the determinant, or I do the eigenvalue. I take the eigenvalue. And actually I want to do both, so that you can see what they both look like. And that way, we get to also refresh our memory on some properties of determinants. So what is the determinant of okay, so maybe it's worth saying that this is an n by n matrix, because I'm going to delete one row and one column, but it's going to look the same. It's just going to be dot, dot, dot. I'm going to draw it in exactly the same way. But the difference is that this one is singular and this one is not.
N minus 1 on the bottom.
Oh, yeah. So this is an n minus 1 by n minus 1 matrix, and this entry is not a minus 1, it's an n minus 1. Okay, so one property of determinants is that if I take one row and I add it to another row, the determinant doesn't change. So I'm going to do that. And actually, I'm going to do that several times. What I'm going to do is that I'm going to add every row to the first row. I can do one at a time to make sure that nothing happens. So what happens when I add every row to the first row? Well, I get n minus 1 plus, I basically get just the sum of all these numbers, right? N minus 1 plus n minus 2 times minus 1. So I get 1. And actually I get 1 in each time, right? Here every column sum is equal to 1. And everything else is intact. Okay. So I did that, and the determinant did not change. Now it's going to seem maybe a little bit strange, but I'm going to do the opposite thing. I'm going to add the first row to every row. And that is also not going to change the determinant. So let's see what happens when I do that. The first row stays the same, and I'm going to add it to the other one. So I add this row to this row. What do I get? 1 plus minus 1 is 0. 1 plus n minus 1 is n. And then here I get 1 plus minus 1 is 0. 1 plus minus 1 is 0. 0, 0, 0. 0. And you see the other ones, like the same thing happens, right? Here I get 0, 0, n, 0. When I add this one to this one, I get 0, 0, 0, n. Okay? And now, maybe this seems very weird, but now you see why I was doing it, because now I have an upper triangular matrix. And when I have an upper triangular matrix, all I have to do is multiply the numbers in the diagonal. So what do I get? N to the n minus 2, right? That's pretty cool. You might not have noticed until now what I was doing. I'm reproving the result from last time. that the number of labeled trees on n vertices, these are just the spanning trees of Kn, and the number of them is n to the n minus 2. So this is another more roundabout proof of that fact. So Chris is going, well, that was really roundabout. It's true that that was really roundabout, and so that's a disadvantage. I mean, I would say that the other proof was nicer, maybe explained more, but the thing is that our other proofs were very specific to this problem. And this technique is going to work much more generally. So, okay, so that was the first proof. That the number of spanning trees is n to the n minus 2. But now I want to show you the other one, which is, what if we just try to find the eigenvalues of the matrix? What are the eigenvalues of that matrix? That matrix is nice enough that maybe we can do it. Now, let me ask you, how do you find the eigenvalues of a matrix? There's one way that we teach our linear algebra students, which is to take the characteristic polynomial, right, determinant of a minus lambda I, and find the roots. Okay. The problem is that that involves, I mean, okay, maybe that works. Actually, that will work through a trick similar to this one. But what's a different way? A different way of finding the eigenvalues of a matrix is to find the eigenvectors. And if I tell you the eigenvectors are these n, they're linearly independent, and then we figure out what the eigenvalues are, then that's a complete list. So that's what I'm going to do. And I'm going to use the fact. This is going to be a little bit easier when I do the following trick. What happens when I subtract n times the identity to this matrix? You just get a bunch of negative ones. So this is ni minus j, where I is the identity, and j is the all ones matrix. And the eigenvectors of this are everything. And so what are the eigenvectors of j? Can you come up with a matrix, with vectors that are eigenvectors for this? So you should take this, multiply it by a vector, and get a multiple of it. Well, let me show you one. E1 minus E2, where these are the unit vectors. So maybe I'll just kind of draw a picture here. So what happens when I multiply this by 1 minus 1, 0? This is E1 minus E2. This times this, 0. This times this, 0. This times this, 0. 0. So this is with an eigenvalue of 0. And just like E1 minus E2 works, also E2 minus E3 works. That also has eigenvalue 0. Up to En minus 1 minus En, that also has eigenvalue 0. So we're almost there. We have n minus 1 eigenvectors. They're clearly linearly independent. Can you find the last eigenvector? Does anybody see it? What happens if I multiply this by the all ones matrix? you're going to get n ones times n ones is going to be n. You're going to get n times the identity. So this has eigenvalue n. Another way of finding this one is that I could have said, well, remember that the trace of the matrix is the sum of the eigenvalues. And the trace is a bunch of ones, that's n. So if all the other eigenvalues are 0, then the last one has to be n. Okay, so then those are eigenvectors of j. But you see now, if you have that j times a vector is lambda v, if v is an eigenvector for j, then I claim that it's also an eigenvector for a matrix. N I minus j times v, how much is that? Well, n times, then a times v is just n times v, minus j times v is lambda v, and so this is n minus lambda times v. Okay. So this is also an eigenvector for this other matrix. So these are the eigenvalues of j, but the same eigenvectors give me eigenvalues of my matrix, Laplacian of Kn, which is ni minus j. And what are they? They are n minus these numbers. N minus 0, 0, n minus 0, n, n minus 0, n minus 0, n minus n, 0. So, therefore, the number of spanning trees, remember the formula tells me that it's 1 over the number of vertices times the product of the eigenvalues that are not 0. So it's n, 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 and how many are there? There's n minus 1 of them. So I get 1 over n times n to the n minus 1, which is n to the n minus 2. And so that's a different method to get the formula. So yes, I wanted to show you the matrix tree theorem. Now, it often goes like this. So the first example that I show you is somehow the one that motivates, but it's not the one that I'm going to really get you excited about, hopefully. So this is cool, but you shouldn't be too impressed because, you know, like Krista said, this is like Krista gestured, this is much harder than our other proofs for this formula. We have 3 proofs, right? We have a bijective proof, we have an analysis proof by Lagrange inversion, and now we have a linear algebra proof. But I hope you'll really be impressed next time when we solve this problem for harder graphs. Because the point is that you could try this for any graph, and in general it's too hard, but when the graphs are nice enough, then you're able to pull off computing the eigenvalues. This is the beginning of something called spectral graph theory, algebraic graph theory. It's a huge subject, and I want to give you a taste of what that looks like. Okay. All right, so I'll see you guys next time.